Hi, I'm Quan. Today I will present our research work about OCR post-correction for Finnish. This is a table of contents, which we will go through this section in following slides. Many researchers in digital humanities are dealing with historical data. The problem that researchers continue to face is the quality of their digitized corpora. While OCR methods have improved in recent times, it is still not always possible to read OCR text. In addition, even the best OCR model will still produce errors. Noisy data make it very difficult for other NLP methods. Many recent post-OCR correction has been developed to resolve the problem. However, most of the methods focus on English, while there are many other languages, like Finnish, hasn't gotten much attention. Furthermore, most of the methods try to correct individual words without considering its context, which is an important feature to exploit. In the recent research, supervised learning gives a good performance on correcting the OCR text. However, this method requires annotated corpus for training. These corpus might not be available for all languages, especially the languages are endangered like Uralic family languages. Our research comes to solve the problem on post-OCR correction for historical Finnish text. But when using the supervised learning methods, there are many challenges. Firstly, it's lacking annotated dataset for Finnish. Secondly, the historical text contains different characters compared to the modern text. Normalized text might be helpful for further research. Also, Finnish has an extremely rich morphology. It also has many compound words, like the word kesar is summer and loma is holiday. But when both words combined into the single word kesar loma, it means summer holiday. The long words with many variants make it very difficult to select the correct form without considering the context. To overcome the difficulties, we propose a novel method which uses synthetic datasets from modern text instead of manual annotated corpus. Next, we will train neural machine translation with a transformer architecture on character level. The model will take error words as an input and try to output correct form of it. We also consider the context of words to the input for the training. We select previous work from Hamalainen and Hanchens as a baseline named Natas. Follow their paper, we set up the same experiments but for Finnish instead of English. The implementation details are mentioned on the paper. The general idea is using word-to-vec model trained on OCR text and using edit distance to filter and build the parallel datasets for neural machine translation training, where the parallel dataset will have inputs are the error words and outputs are the correct words. Both word sets are extracted from the word-to-vec model vocabulary. Even the Natas is very simple to set up and give a good performance on non-rich morphology language like English. It is also having many cons. Mostly it due to noisy in the extracting parallel dataset due to unsupervised tasks. The word pair for training NMT model is very limited. Now we go back to our solution. First step, we construct the artificial datasets in different ways. Modern Finnish corpus Yle News contains more than 7,000 articles are chosen to create artificial errors on text. There are two ways to introduce errors. First is using a random generator. The idea is, for each word in the dataset, manipulate errors to that word by deleting, replacing, and adding characters randomly. We only modifying alphabet characters and the number of characters being altered depend on the length of the word and also depend on a noise rate, so that a longer word tend to have more errors. Next is a trained generator. So instead of using a random generator, we will try to train a model which mimics the OCR errors. To do that, we use a parallel dataset from NASA's experiments. We train a simple NMT model in a reserved way. So the input will be the correct words and the model will output an error word. The custom loss function is needed in this case because for one given correct word, we want to output multiple variants of error words. The purpose of the inverted cross-validation, as you can see in the formula here, is to punish the model if it outputs the error words identical to the correct words from the input. After having the parallel data, next we will train transformer model which take artificial error words and its context as the input and label is the correct word. The key of our model is in the data format. We format inputs as follows, where we use a window of words as input. In this window, the middle word will be the target and it is modified to the wrong word. The left and right context are kept in correct form. The label is the correct word of the target. We need some special indicators so sequence-to-sequence model knows where is the start of sequence, where is the separator of context, where is the target, and the end of the sequence. Further, if we train different word lengths in mini-batch, a padding indicator is needed. So we set up our experiments as follows. With 3 different window size of 1, 3, and 5 words. As mentioned earlier, the target word is the middle word of window. So in case window size of 1, there is no context for the target word. For example, in the sentence, the quick brown fox jumped over the lazy dog. The word browse is modified to be found, which is incorrect one, and the label for it is browse. These words will be given artificial errors by either random generator or a trained generator. So with 2 error generators and 3 window size, we have total 6 models for experiments, where TF means transformer, RAN means random generator, and trains mean trained generator, and W stands for the window size. For the training, we train the sequence-to-sequence models by using transformer architectures. We apply a novel approach for the training. So for every mini-batch iteration, new random error words are generated on fly. That means it prevents repeating words for the model, and model always sees some fresh errors form. We stop the training after the loss is converged. In evaluation, we use ground truth from historical Finnish newspaper. This dataset has more than 400,000 of ground truth words and 3 different OCR methods, which is the Tesseract, O, and FR11. We will evaluate 6 proposed models and the baseline performance based on the word level instead of character level for each OCR method. The initial results show that there is no improvement on the OCR text. After analyzing, we found that many words had been normalized to modern Finnish. So the comparison with the ground truth is marked as false. For example, in this case, both are valid, but the W letter is changed to V letter on modern Finnish. Because there are a large proportion of W letter changed to V letters in modern Finnish. Due to these normalizing issues, we decide to replace back all the letter V to the letter W. After that, only the words past the Uralic NLP tool check is accepted. And we can see the result is improved significantly. But in the case of Tesseract OCR methods, where the accuracy of OCR text is very high, which is 88%, the model is able to fix the error words, but it also gives some wrong prediction on the already corrected words. So the accuracy in general is 84%, which is less than the 88% as in the original text. But when we do the same process for old methods, the results is now outperform the original OCR text 3.92% on the best model. It is able to fix a lot of error words. By looking to the table, we can see the synthetic datasets with transformer models outperform the baseline data. The trained error generator outperforms the random generator. And the context windows have to improve the result noticeably. The result is showing the same for FR11. The result is now outperform the original OCR text by 3.71% on the best model. This is significant, and again, our methods seem to outperform the baseline on every aspect. After analyzing the errors, we found some interesting problems. For example, firstly, in some cases, due to our character level training, models make up words that do not exist. Secondly, many words has been normalized to modern Finnish, which affects the accuracy on word level. Another problem is Uralic NLP tool filter out non-Finnish words not on the purpose in some case. For example, you can see the Uralic NLP reject the word method star vorticen just because of the line break split the original words to coil and method star vorticen. Word level also is very tough metric. So one wrong character leads to the whole word being wrong. Especially it's tough on Finnish because the Finnish has very long words. So in summarize, our methods is able to improve the OCR text quality, and also it can normalize text to modern Finnish. The synthetic dataset and transformer models outperform the baseline, and it has very potential for the further research. A trained error generator is better than a random error generator. Context window have to improve the results. The method doesn't require annotated datasets, which is fully unsupervised. For the future works, we need to improve the method so that it will gain the accuracy on an already good OCR text, like in the Tesseract case. And thank you. Any question?